before we start, I have to give you some confession. I learned to speak in Israel, and in Israel, the audience have practically no inhibition of interrupting in the middle of the conversation. This is how I learn to talk, and this is how I feel most comfortable. Now, I am aware that in Europe, a lot of people feel that this is rude to interrupt a speaker. Not only don't I feel that this is rude, I also brought some gift for the people who actually do interrupt me. Okay? So this talk is about how you should never write your own database. And I speak as someone who have done that quite often. Those three on the top are actually, I've built them, deployed them to production, they're used commercially. In particular, RavenDB is a document database for .NET and other languages, which gives you NoSQL capabilities. That puts me at a rather interesting position of telling you all about where the pain point in actually trying to make something like this happen for you. I've also done a bunch of other stuff, but they're not that interesting. So this is what I want you to take from this session, okay? Mostly that building database is actually really, really hard. Yeah, I'm really sorry about this guy. So building database is really, really hard, and you know what? Let's build one. Let's build a NoSQL key value store database. I have done so. Here it is. This is using the Web API controller. And as you can see, this is just an endpoint that exposes three verbs: get, put, and delete. This is all you need to actually get a viable key value store system. Key value store system is basically some server somewhere that just given a key, store a value, and when you request the value for that key, you get it back. So this is it. All of that is based on the lovely concurrent dictionary that we have here, so we have really very little work to do. So this is the server side. Please take a moment to read this code. Anyone has any comments about this code? There is a free shirt if you do. Wow, I can't even bribe you to talk to me. Okay, so this is the server-side code. And let's see, so we have the server side, but we also have the client side. Now, what do you know about NoSQL? Give me stuff that pops to mind when you hear NoSQL. Yes? MapReduce. Okay, what's more? Sharding. Please don't bother to raise your hand, just shout. More. So MapReduce, sharding, what else? Scale out, right? Large amount of data. Can this handle a large amount of data? Sorry? Not really. So you say it can't handle a large amount of data. I'm saying that I can get a production machine right now with 192 gigabytes of RAM, at which point I think this can handle a lot of data. But you know what? You're absolutely correct. This is still not enough. I need to do sharding. I need to do scale out. Here is my scale out solution. And shirt size? You and you and you. Shirt sizes. Medium? Or large and? Okay. So let's try it. In the meantime, do you read this? Can someone tell me what this code is doing? Does someone want to share? Come on, guys, I need some response. Anyone? So we are hashing the keys and doing what? So look at this. We start here. We get a list of URLs, and we just create HTTP clients for those URLs. Wherever we make a request, we're getting the key, get the hash code, modulus the length. So based on the size, the number of clients that we have, we decide which client you're going to go to based on the key. Based on that, we make the request. So what is this code doing again? Sorry? Okay. What is this called? Consistent reader hashing, okay. Actually, it's about the most horrible hashing algorithm you can think of, but we'll ignore that. But we spoke about other things. Well, obviously it's not MapReduce, but what is it? This is sharding. This is us doing sharding. This is us going into scale-out mode. Think about it. Right now, I get 5 machines with 64 gigabytes of memory on them, and I can store half a terabyte of information, more or less, let's say, and I can keep it in RAM. So what is going to be my read speed? Basically 0. Maybe I have to pay some heat for making the web request, but that's okay. Guys, 1, 2, and we have what? We have a NoSQL database. It's that easy. Honestly, it's that easy. Anyone wants to go with this to production? Sorry? I can't hear you. We don't have security. Sorry? Failover. There is no what? No seeking? No synchronization, yes. So in this case, each database is absolutely independent, and we only combine them together from the client side. No security. What else? Sorry? Transactions. Actually, we have transactions. Would you believe it? This code is transactional. Wait, is this? Yeah, that's the code. This is transactional. Either you're successfully removing the value from the dictionary or updating the value in the dictionary, or you're not. This is transactional. Well, not really. Because here's the problem. Okay? When we talk about those sort of things, we talk about usually ACID. What is ACID? Atomic, consistent, isolated, durable. Okay. So we actually have transactions here for a single key. What happens if we wanted to have transaction for 2 keys at the same time? Can we do that? No. So here is something interesting that you might want to know. This is still more actual database than many NoSQL databases. There are databases that won't even observe the single transaction on a single key. But we'll touch on that later. Let's talk about the client, because right now this is much easier. So the client, we talked about hashing. What's the problem with the hashing the way I did it? Look at this. I'm relying on get hash code. Interesting fact. Get hash code is not stable. It's not stable between 64 and 32 bits. It's not stable between different versions of the .NET framework. But you know what? Let's say that I have a way to hash. I'm using MD5. That's stable. That's known. So what's still the problem in here? Sorry? The location of a value is dependent on the positions and the length of the URLs that we get. What happens if we want to scale out again? We used to have 3 servers, now we want 4. What's going to happen? All our hashing decisions just went down the crapper. This is where we start introducing things like virtual shards. This is where we're going to start talking about ring buffers. All bunch of really interesting things if you're mathematicians or if you really, really like self-mutilation, because this is what happened to your brain when you start reading too much of that. Okay, so let's talk about high availability. Do we have any? What happens if a server goes down? Anyone? If one of my servers goes down, what happens? Sorry? You lose all of the data on that server. By the way, here's a tricky note. Let's say that I'm running this on IIS. By default, after 20 minutes of inactivity, it will reset my database. But let's say we don't care about that. We never have 20 minutes of inactivity. By default, every 29 hours, it will reset my database, losing all of the data. Anyone here have ever had a system that was up for 3 years, 1 year, 3 months, 3 days? Okay? It doesn't really matter what system you're talking about. If you're talking about Linux or Windows, cycle time for databases is usually in the order of several months. So we really have to plan for that. This is without even starting to talk about how we are going to plan for failures. There is a lot of very, very interesting failure scenarios. When I have 3 nodes in the system, and some of my clients can talk to this guy, some of my clients can talk to this guy, and this guy can't talk to this guy, that's going to produce some really interesting behavior that I actually have to account for and work with. That's really harsh. So we talked about adding a node to the cluster. But you know what? Clients, I don't care about clients. I build databases for a living. That's actually what I do. But, and actually I do care a lot about clients, but the problems of the client size are basically nothing. The first thing that we need to worry about is persistence. Are we going to have any? Where are we going to usually persist the information? Into disk. How? Now we have to realize, okay, there are 2 common types of disks today. We have the spinning disk. This is usually standard HDDs, hard disk drive, and they range from rotation speeds of 5,400 for slow, cheap laptop drives to 15,000 RPMs for high-end server drives. The problem with having a spinning component in the hard disk is what? What's the problem with the fact that there is an actual spindle? Sorry? Sorry? Heat, okay. I don't care, that's the hardware engineer problem. Latency. More specifically, there is a big, big, big difference with the performance of the system relating to where I'm putting the data. Okay, so let's imagine that this is the disk, and let's say that this is a circle. If I'm putting the data here and then here, it's very easy for me to just read this and read this. If one portion of the data is here and one portion of the data is here, what's going to happen? I'm going to have read here, then scan all of that and read here. Worse than that is if data A is here, data B is here. I may have to do the entire scan or may have to stop and restart. And someone is going after me with a machete afterward. Anyway, so problem number 1 with HDDs. Another problem is This is for random reads. So when we read from HDD, we really want to do sequential reads because this is the fastest way that we can go about it. The problem with that is that it's really hard. How do you create data in such a way that you can actually do sequential reads? But you know what? Let's avoid reads for a second. Let's talk about writes, because this is what persistence is all about. So when we persist data to the disk, where are we actually going to put it? Again, random writes are horrible performance killer. If you need to scan and update something here, and then here, and then here, and then there, that's going to kill your performance. So we really want to be able to do sequential writes. That means that we're always going to write to the end of the file. That's good, but that's still not that good, because now we get into another interesting problem, is that hard disk manufacturers will absolutely lie to you. When you write, when you do something like file.write, what do you think actually happens? Anyone? The data goes into a buffer. If you're working in .NET, in Java, Ruby, it goes into a buffer that is managed by the framework that you're using. The operating system doesn't even know about it. Afterward, it goes into a buffer managed by the operating system. Afterward, this is queued to be sent to the disk controller. At that point, the disk controller may decide, I want to save the data, or I may not want to save the data, and maybe just keep the data around its own memory. So we have to be aware that the disk, we actually wrote something to disk, someone hit the power button, and no data in there, none at all. We haven't even talked about the other type of a hard disk, which is solid-state drives. They are wonderful for random reads, random writes, sequential reads, sequential writes. Everyone is happy, right? Two problems. One, they are really expensive. Two, they have a very interesting problem. If you make too much writes to a specific sector on the disk, you kill it. Yay! So this is just talking about persistence. I haven't talked about how to actually implement ACID. I haven't talked about, okay, how do I handle transactions? What happens if I want to have a transaction that is composed of multiple values on multiple nodes? Is it even possible? As it turns out, no, this is not possible. We still try to do it. Usually shoot ourselves in the foot. We have concurrency. How do we deal with two people trying to modify the same value at the same time? Queries. What sort of query could we do with the previous example? Just by the key. But what if I want to ask questions such as, give me all of the users who have signed in the last 5 days? This has actually turned out to be a really hard problem, because you may have 15 servers and the data is spread across all of them. So you now need to split the data. Maybe you have some sort of a sharding factor, a whole bunch of stuff like that. We haven't talked about memory usage or IO usage. And what happens when you're coming under load? That's really, really going to kill your application if you're not careful. And finally, this is the problem. As you've seen, it's really, really easy to get started, and then it sucks you down, and then you have to deal with all of those problems. Okay, just some things. This is mine, okay? And I've been working on that since 2008. We are right now in the process of making the 2.5 release. This is a RavenDB, which is a document database, and this is what the UI looks like. This is the Northwind database. And as you can see, the data that we store here is actually stored in document form. hence the name document database. And the interesting thing about it is that because you store data in document form, you can actually store data that is arbitrarily complex. Okay? And we can even take this and say, you know what? Let's make a query, a dynamic query, on orders. And notice what I'm doing here. I'm saying, give me all of the orders, lines that have product, which is product number 10. Okay? So just to give you some idea, this is done on a unstructured data. And this is done in a way that is really good to work on for production. So when you go to production, you don't have, oh my God, what just happened? There's a bunch of other stuff. This is key value store, key value stores like the one that we have created. Graph databases that are mostly used for social and graph questions. For example, find me the friends of my friends that are not my friends, or find me the path from me to you through all of the people that we commonly know. And those sorts of things. Big tables are usually used if you need to store hundreds of terabytes or petabytes of information, and you still want to actually be able to access them. And we've done the demo. I'm really sorry, I don't have a lot of time. I think I'm already running over. So this is the time for questions. And start the question by specifying your shirt size. Wow, you're a tough crowd. Yeah. Mm-hmm. I'm sorry, you have to raise your voice.
You talked about graph database. You put into graph database also the triple stores or RDF systems. Yes.
RDF systems are a branch of document database or graph database, depending on where they lean, whatever they give you, graph operations or mostly document operations. They tend to be relatively rare. RDF was pretty big in about 5 to 7 years ago, and pretty much, you don't hear a lot about it.
Okay. And
yes.
Okay. Second question.
Yes.
The systems like Elasticsearch.
System like what?
Elasticsearch.
Yes.
Will you consider it a No SQL database?
Yes. Almost, because it's not actually a database per se. It's not storing the actual information. It's just the search for information that is stored elsewhere. So the major difference between auxiliary indexes and databases in my eyes is where do you actually store the information. And if you actually store the information inside a system and this is the master copy, that would be a database. If it's just, Elasticsearch, you can store documents there and do a lot of searches over them, but this is never the master copy. Okay. Yeah. Okay. More questions? Yes.
In the RavenDB logo, there is a catchphrase saying that it's second generation NoSQL database.
Yes.
I just want to know what are the main difference between first generation and second generation.
Okay. So the major reason that we call RavenDB a second generation database is that we started this relatively late in 2008, 2009. And at the time, there were two important document databases, CouchDB and MongoDB. And the basic idea is that we looked at the environment and said, you know what, this is really interesting conceptually, and I personally have gone through every single line of code of the CouchDB, of the CouchDB code base. And it's really interesting what they're doing. The only problem is they're doing some things in ways that make it really, really hard to actually work with the data. Actually work with the database. For example, the thing that I just did with querying the data, this is not possible to do in CouchDB, sorry. CouchDB would require you to first define the data that you want. Define an indexing function to that, and only then you can query on that. This is really interesting idea. It gives you some nice performance, but it means that from development perspective, I need this data. Okay, now I have to go and write this function, and instead of just making the query and getting the results, I have to go into the entire process of developing something new. I think that this is insane. So RavenDB doesn't require you to do so. RavenDB actually, if we go and look, you can see what happens. We made a query in RavenDB, and that query created this index. You see? And this index is an auto index maintained by RavenDB. And that means that this is maintained by RavenDB. If you make additional queries on lines for products, you will get that. But it also means that over time, RavenDB says, okay, there are no queries on this index, I'm going to kill it. Or maybe I'm going to merge it with additional indexes. This gives us a lot more power, a lot more flexibility in how we're actually working with the data. Okay, so there's a lot of stuff like that, stuff where maybe the basic functionality is the same, but we remove all of the sharp edges. We streamline the entire operation. Trivial example would be that I can take this data and tell RavenDB, look, you have data inside that is in document form, that is arbitrarily complex. Take that information, replicate that to a relational database in a relational forms, and it can do that. And that's the basic idea. That's why we call it a second generation database. More questions? Going once, going twice. I still have a bunch. Okay, yeah. Sorry, didn't see you. Okay, so the question here is, what is the validation model in RavenDB? And I don't understand the question. I think that you're asking whatever it has schema. Is that the question? So please, you have a mic?
In case, is it a distributed or distributable database?
Yes, it is distributed database.
So you have to design validation model for currency, for acidity, etc.
For what?
For requests that are coming to different.
No, you don't.
sources. Why?
You don't have to do that. The basically, so you're talking. I think that you're talking about what is the consistency model, in the sense. Okay, so the basic idea is that RavenDB is acid, in the absolute sense that if you wrote something to RavenDB, it's going to be kept there. It's acid across a single document, multiple documents. You can even run a transaction across multiple nodes. When you query RavenDB, there is an aspect of eventual consistency. And this is different if you actually go and ask, give me document by name, versus give me all the document where that have a product of product state or something like that. Okay? So we have both models, and you're free to choose which one you want. One of them is very accurate and immediate, but it's relatively limited in the type of queries that you can do. Basically, give me the document by the ID or by ID range, or you can do a lot of interesting queries, MapReduce, spatial, full text search, all of those sorts of things, but we process them in the background and they are eventually consistent. From your perspective as the client caller, you don't care about this. You just write the code and it works. Okay, because the client code usually take care of all of that. And guys, I think this is enough for open questions. Feel free to come to me. I still have a bunch of shirts to give out. So thank you very much.